Hey everyone, thank you for coming. I'm glad to see familiar faces joining in today. Today we're going to kill some serialization overhead and complexity. I hope you're all kind of hungry for some non-piece working lecture. Let's start by just saying first, what exactly is object serialization? So object serialization is basically turning C++ objects into a sequence of bytes. The reverse is often called deserialization, where you take the sequence of bytes and make them again into an object. And the reason is basically because all the time, like more often than none, we basically want to send objects over the network, but we can't just send them as they are represented in memory. We need to first go through converting them into bytes. We send them over the network. We store them in a file. We use that to communicate efficiently between different programs and so on. I would like to review some statements about C++ serialization, and let's review them and see whether they are true or not. The first thing is that object serialization in modern C++ has zero runtime overhead. Now, we're all here to do zero overhead stuff, so that's like one of the major pillars of C++. But, you know, maybe we don't need to answer this question on ourselves. I can tell you that even before this talk, when I go and review online for serialization libraries, there are many serialization libraries written even by corporates, so they must be good, right? And those serialization libraries, as common as they are on the internet, so there are also benchmarks on the internet that we can check for. So I've prepared for you some benchmark to look at, and maybe there will be more later, and let's see what we can understand from it. So as you can see, first of all, I like to call this benchmark the monster benchmark, because it's got the monster at the bottom. And the purpose is basically to test various serialization libraries and a few of the more recognized ones, I can say. And let's just, I guess, see how well they do when you serialize a vector of monsters. So I really don't want to get into the details of this benchmark. That's why I kind of gave you the URL to look at after. But I do want to point out that some of the results that we can see in this benchmark clearly say that they can't all be zero overhead. So look at this. There is one library that takes many more seconds. Like even if I go for Boost or Protobuf, they take many more seconds than the first two libraries. Maybe the first two libraries are zero overhead, but I guess they can't all be zero overhead. And that's like part of the issue that we're going to handle in today's talk. As it turns out, not only some of the libraries are not zero overhead, but the benchmark author here also provided a handwritten example, which he later measured. And as it turns out, it is faster than all of the above libraries, which means that, hey, there is some overhead to those libraries. So they can't be zero overhead. And that's motivating me to kind of do this lecture here. Now, what is this talk going to do? So I'm not going to tell you just yet, but we will do it together, and soon enough, we will discover what can we do better than what we see on this slide. Hey, another statement is, I can't afford to use C++ serialization because it would not fit my embedded system. And there is two parts for this. One is that, hey, embedded systems more often than likely to not have enough room for exceptions. Almost every library that I showed before rely on exceptions to do error checking. And we can't afford to not do error checking, because then it will be like a little bit unsecure, because maybe somebody can overflow my data buffer. I don't know. I need to do some kind of error checking. But I can't rely 100% on exceptions. Another thing is, what is the library size? Maybe, let's assume the library doesn't even use exceptions, but what is the size of the library? Can I fit a couple of megabytes in my embedded system? Maybe not. But I can definitely take the monster from the slide before and serialize it by hand. It will certainly not be 2 megabytes. So here is like another time the same benchmark, but this time I'm using like different details or different data points from the benchmark. As it turns out, the benchmark author also submitted the size of the resulting benchmark binary. So each kind of library is compiled into a different binary. And finally, here is the size in front of our eyes. And you can see that some libraries take significantly more than other libraries. And this is important because we can't really make, if we're here all to make some solution to this, we can't go for like the 2 megabyte solution. We need to do something a little bit better. Hey, so by hand, this like took a little bit less than the rest of the libraries. It was like 43 kilobytes. But I'm sure like we can do better than that. And this talk, although I'm not giving the details now, we will see what it can do later. OK, so what is this talk that I'm talking about in all of these slides? So this talk is born from the CppBits library. It's a library that I wrote to basically experiment with data serialization and trying to solve this problem that I'm showing to you. And if the title of the presentation didn't like hint this, then this surely will. We're going to start by beating our favorite C++ serialization libraries. And we're going to do so in benchmarks that we didn't write. So somebody else wrote a benchmark, and we're just going to participate in that and see. Does this statement clarify that I'm not here in peace? OK. So hey, we're not going to just do it. We're going to do it in a way that is going to be simple to use. We're not going to require almost always from anyone to add any lines to their classes. We're going to not pay for what we don't use. Surely you've heard of C++ serialization libraries that have like extra features such as, hey, compatibility, hey, I want to do cross-language communication. We're going to allow it. I don't know if we will get there. I will point you definitely for the repository to take a look at this. But we are going to allow an opt-in to that feature. We're not going to mandate the compatibility. We're not going to mandate any extra overhead. Hey, so the thing about serialization is that is like used very often to actually call functions in a remote program. So I don't want us people to kind of implement a serialization library and then go, oh, but we can't use it to communicate in an efficient way between processes, programs, or computers, or systems, or whatnot. It's going to be zero overhead. So that means to me that we can't write it better by hand, unless somebody shows like a counterexample, which is very likely, but I don't know if we'll be able to do it during the talk. Yes, we're going to try it. And the best part is not the zero overhead part. The best part in my mind is that we're going to leave no room for a lower level language. And all of this will work on completely freestanding, embedded, without exceptions. With or without exceptions, I will say, because exceptions do make our code a lot better sometimes, but I'm not going to require exceptions. OK, so who I am, my name is Eyal Zedaka. I'm a technical leader in C++, operating systems, and software security. I recently joined Microsoft, very recently, so I'll not elaborate on that a lot because I don't have what to. I'm a C++ lecturer on invite basis from time to time, and such as like CppCon like 2021, where I talked about using coroutines to implement exceptions in freestanding environments. So you must understand that freestanding is kind of dear to my heart. And I have some open source which you can take a look later. And I guess that's all for that slide. So this is like the same benchmark from before, only this time I'm going to show you the results. And I want, like, the reason I'm showing it right now is because I think it's super important to learn the lesson that's going to show on the screen very soon, right at the beginning of the talk. So even though somebody wrote a handwritten code, it doesn't mean that it has no overhead. So if you want to write handwritten code and actually later compare it and use it for benchmark, that's fine. But if you want to guarantee that this is zero overhead, you must do it with introspection, with compiler explorer, with something that will help you make sure that you're really getting into the zero overhead point. And I think what I'm going to show is, hey, we're going to be able, everybody here is going to be able to reach the zero overhead point because there's no secret. Like when I think it was this person, when I submitted a pull request to this benchmark, he asked me, hey, what's your secret? So that's when I decided to kind of say, hey, there's no secret, let's do a talk about it. So it's going to be very simple, everybody's going to be able to understand it. Okay, here's another benchmark. And again, I don't want you guys reading all of it, I'll just give you the result. Hey, I think what's special about this benchmark and why I gave it is because this benchmark, even though I didn't write it, I can tell just from the middle, wow, this is like laggy a bit, but it has like two kind of, actually three, zero copy libraries except like flat buffers, even though zero copy, I think this benchmark is doing some kind of translation between the flat buffer representation and the C++ representation. But at least two are given like 0 millisecond to deserialize. So that's amazing. And even though they take 0 seconds to deserialize and ZPP bits is not a zero copy library, it's still gonna beat them if you talk about both serialize and deserialize together. And I think zero copy is great and you should use it, but I guess not all the time because it comes with some kind of cost of, hey, the library is going to be a little bit more complicated. Maybe the usage is going to be a little bit more complicated. I think not always it's worth trading this. And yet another benchmark, and I'm going to jump straight to the results again. Here, there's a couple of libraries that are being measured. I'm just pasting it here so you guys can check it out later. OK, let's just go ahead and discuss how we are exactly use this library. So I already told you what it performs like, but I didn't tell you how to use it. So let's say we have this data structure here. It is an address book. I took this example from actually Protobuf documentation page, and I thought, why not translate it into C++? And basically, what we're going to do in ZPP bits is actually, let's build a Protobuf file and let's generate C++ code from this Protobuf file, and then use that C++ code, add it to, like, add an extra build step to a build system, and everybody's going to be happy. OK, so no. The reason I didn't go for something like that is because of two things. One is this introduces some kind of unnecessary friction in my mind. It is kind of going outside the language. And I don't think that going outside the language CppCon is a good idea. And I don't think it's frankly a good idea also to use in your project if you're coding in C++ and then you need to go out of it to just do serialization. It doesn't seem fair. So we're not going to do it. We're going to do this instead, right? So what is this instead? This means like, hey, let me, because I don't know how to iterate my members, I will just create some visitor. And then I'll put all my members in, and somehow in a recursive way, all of it will get serialized. That's fair, except, no, we're not going to do it. But more importantly, we're not going to do it because this returns void. So how can we return void and not use exceptions? So hey, we're not going to do it. And that's exactly what I said. Not using exceptions, and unnecessary friction again, because you need to type all your members. So how do we use ZPP bits for real? We just do nothing, OK? That's like your same classes that you're used to working with. You just most likely need to do nothing to them and just work as it is. But really, I'm not going to discuss now how I do this, but I will discuss it a little bit later and point you to some interesting places where you can read about it. But how do I really serialize? Now, let's say we have a serialize and deserialize function. We absolutely don't need to like define those functions. I'm just showing this as a kind of tool to help describe how to do it. So the serialize will basically just use something called ZPP bits out. That's like an output archive, and that's going to take some data, and it's going to populate the data with your object. The way you populate the data with your objects, you first output the object via the call operator, and then immediately check for failure. If you use return values, if you use exceptions, you can use something else. And it's kind of the same when you do the deserialization, because now you use a different type of archive, the input archive, which takes the bytes and puts them into the object. Let's compile this, because I think it's very important right at the beginning to see what kind of assembly we get, so we can then learn from it and apply it when we ourselves going to implement this code. So here is the assembly. I don't know if everybody can see everything, but I'm going to just talk about the important criteria of this assembly. So on the right side, we can see the serialize function. And as I scroll down and look at this function, I'm trying to find some kind of function calls. And I see a memcopy here. I see another memcopy, okay, another memcopy, and the function is done. Okay, so no function calls to anything. This was just doing some kind of bit manipulations, bits and bytes manipulations, better to say, and some memcopies, and it's done. Surely you must know that we can't just memcopy like the entire address book, because we have stored strings in there and stuff like that. But somehow we got the assembly to do it in 130 lines, I think. And we have some data here on how long it took. So if I can just scroll down to show you the main function, it's going to do like a serialize, a deserialize, and then immediately it's going to compare to see that it's equal. So here you can see some address book is initialized. You can see an empty one, and then we compare. And it prints some kind of data here on the right side. It prints how much the size was. The size is 134 bytes. It's equal. And we have a little unprofessional, I should say, benchmark. That's why we have other people to do benchmarks. So it's an unprofessional kind of benchmark to give us some idea how long it took to do 10 million times the deserialize, and it took like 830 milliseconds. I think that's fair. We can also look at the deserialize function. It's going to be like more or less the same, except there's some function calls to resizing of the vector, because the vector is initially empty and you need to resize it, or however data you have. I think you guys can check it out later. So this is like giving us a good idea of how the serialization looks like with ZPP bits, but hey, this is not guaranteeing zero overhead. To guarantee that this is zero overhead, or almost guarantee, or get closer to it, we need to experiment with handwritten code. But before that, I would like to talk about the format, because I didn't discuss it with you yet. The format is going to be very, very simple. Every time you see something that is not fixed size, it's going to put the size in front. And then immediately it's going to serialize the data. So for string, it's going to be size and then the bytes of the string. In this particular example, the address book is of size 2, like the vector inside the address book. Then there is 2 people in there. The first person basically has a name. So the size is before. The ID is fixed size. Again, something with size, the email. Again, the phones, there's 2 phones in there, and 1 phone number is this. And the type is mobile, and then there's another phone. So you get the idea. It's very, very simple protocol. If you will read the repo, you will see that once I give you the link, you can customize this a little bit. But we're not going to discuss it now. But how can we prove the zero overhead? Let's write some handwritten code, okay? Our handwritten code is going to look like this. Notice that there is a lambda called out. This lambda will accept something. It can be like a vector. It can be like a fundamental type. And then it will do a memcopy. I will show it later. But the most important part is that right after we define this lambda, we immediately call it for everything that we want to serialize. We serialize the size of the address book. Then we go for each entry. We serialize all of the members. And once again, we go for the phones. We serialize the size. And you get the idea. How does the lambda look like? Well, it looks something like this. This is not the most idiomatic code that you will ever see. This is like to basically fit the slide. The lambda is distinguishing between a string and a vector, even though right now I'm kind of talking only about vectors of fundamental type, so it's not going to be like a vector of phones, because for that we need to decompose it manually. And it's probably not the right way to check whether vector or string. You should probably use like a stud ranges concept or something like that. This is just for simplicity, okay? So the first thing we do is, if we're not a vector or a string, according to this example, we must be something like a fundamental type, in which case we serialize the size with memcopy. Sorry, we serialize the fundamental type with no size because it's fixed size. And for the vector and string case, we need to serialize the size first. We need to calculate how many bytes and then serialize that many bytes into the data. And that's it, basically. A very simple example. I do have some, how do I call it? So I do have some error checks here and there. The reason for the error checks is we don't want to write unsafe code. You can always get rid of it with ifconst_expr if you want to write unsafe code and just play with it. But I decided to leave them in. And let's now see the difference between the two. So on the left side is the handwritten code. On the right side is the ZPP bits code. And let's see what Compiler Explorers thinks about that. And I will read you some of the details because it's like a little bit hard to read. The size on the left side, the handwritten code, is 178 bytes. On the right-hand side, it's also 178 bytes. And those with a keen eye must have noticed that here I'm asking explicitly the ZPP bits to serialize each size as an 8-byte type so that the comparison is fair. By default, it uses 4-byte size. And we have also information that tells us the code is correct because the serialization, deserialization is equal. And we get more or less the same kind of result in terms of millisecond. This is like 851 millisecond. This is 853 millisecond. That must mean that we're not zero overhead because the handwritten code beat us by 2 milliseconds, right? We're not zero overhead. Let's try to run it again. OK, we got lucky. It's 827 milliseconds. So now we beat the handwritten code. But what does that mean? So to understand, we need to stop measuring stuff and start looking. So let's look. Let's go to diff view here. Let's put some flags here. And actually, for this to be more like easy, I will disable the main function so you can just focus on the serialize, deserialize. And here are all the differences. It looks like a lot of the code is same. And then we get to that point. You see an instruction moved. OK, instruction moved again. Another instruction moved. And we are at the deserialize already. Let's go down. OK, some similar instructions. OK, so it's fair to say at this point pretty confidently that we wrote handwritten code. And the code was like, we didn't find some overhead in there, except maybe like the error check or something like that. But hey, we can get rid of error checks from both sides. So to do a fair comparison, we probably get the same result. So we get the same exact assembly, maybe a few instructions moved. But I think it's pretty kind of, I'm pretty confident saying that we reached the zero overhead point. I don't know about you. OK. Let's go a little bit further. Let's discuss what kind of toolbox ZPP bits uses to be zero overhead. So here's the serialize, deserialize again. And the first thing you want to do is make sure that everything can inline as best as possible. Because as you can see in the assembly from a few slides before, we see only calls to memcopy, maybe. We don't see nothing else. Maybe a call to vector resize or something. We don't see like any call to recursive serialization logic, because that would be costly. By the way, another tip is if we make everything inline and templated and nice, we should also go for const_expr, because even though most of my slides don't have the const_expr keyword, expect it to be there in the real code base. I just trimmed it down for you. And really the only thing that was not const_expr is maybe the memcopy, and that can be overcome with using of bitcast, which I may show in this presentation, I think. And the second important thing is, hey, no virtual functions, because even though virtual functions can be devirtualized and all this kind of stuff, we don't need it to solve this problem. And if we don't need it, why should we risk the compiler doing bad stuff? So let's not do it. Hey, let's use concepts and templates to be fully generic. You can see the reason the code is there is that even though there is a span in there, it could equally be an array. It could equally be another vector or string. So we don't really care as long as it satisfies our concepts, and we don't want users to start converting between the different types. And hey, we want to customize and optimize by if const_expr. You can imagine that when you write a serialization library, you will get some kind of issue where one of your templates is doing a range base 4 over a std string, and then trying to memcopy each byte separately. This is the kind of stuff that the compiler knows how to optimize. So usually what you will expect to see is like a huge memcopy implementation inlined instead of the for loop. But to avoid this like huge inlining, which costs us a little bit in code size, we can just detect that with if const_expr. Hey, if const_expr we're serializing like a continuous range of, I guess, like trivially copyable, maybe we can do something about it and do a memcopy instead. There is like an edge case we need to pay attention for padding, but yeah, that's like the general approach. There is more stuff in there, but I'm just gonna elegantly skip it. The zero overhead error handling is the kind of thing where you want to probably use return values. I'm saying probably because, hey, remember we are going freestanding. It's not that exceptions can't be zero overhead, but because we're being freestanding, we want to be embedded friendly, we're just gonna use return values. And then the return values, we can offer alternatives for them by using like a function that checks the return value or throws, okay? So you don't need to check manually. You just need to put the or throw there. Or you can go watch my last year talk about how to implement exceptions with coroutines, and then this co-wait will also work in freestanding and will just kind of emulate exceptions for you in a zero overhead way. Very nice. Okay, so let's implement our own C++ serializer. The reason we discussed all of this principle is because I'm just going to quickly show how simple it is, and I may do it a little bit fast, but if it's a little bit fast for you, you can just later watch it. It's not like big deal, it's like a few lines of code. So the interface is gonna be a little bit different this time because I want to be able to feed the slides. It's not gonna be an input and output archive separately. It's gonna be just one archive. It's gonna know if it's input or output because of the parameter that we send there. And now we just add again the serialized member functions. And the reason that I'm adding this is because I'm not yet implementing the reflection part of this. I'm just gonna show you how you do it zero overhead, and then we can talk about reflection. So, hey, this is the archive class that we are going to build. It's going to have some very easy to understand functions, such as the constructor. It's going to have position. It's going to have a call operator. Here is where it gets a little bit nasty. So you need to somehow separate all the parameters that you want to serialize. You can do it all together. You need to kind of each one serialize separately. And I chose to do it via recursion because I know fold expression, but because we're checking errors, there is a way to check errors and do fold expression, but it's going to be like too kind of meta-programming. So I just decided to do it like this, and hopefully the compiler is going to inline it, and everything will be fine. And then we have an empty serialize many and serialize one, and all of the work is really done in the serialize one, which gets something and then serializes it. That's the most important part. Okay, so here's the serialize one. So we begin by checking for fundamental type or enumeration type. We can check for trivially copyable types as well, but again, there's some issue with the padding. We need to be a little bit careful with that. You can do that, but I don't go for it for now. So hey, when we have a fundamental type or enumeration type, all we need to do is just a simple memcopy, and this serialized bytes off is just the kind of memcopy that goes one direction or the other direction, depending whether we are inputting or outputting data, whether we're serializing or deserializing data. That's all. Then we're going to check if we have some kind of container thing. Again, not a proper way to check, but simple enough for us to show. If something has data and size, then we're just going to treat it as a vector or string or something like that. And then we are going to basically, if we are, OK, we're going to serialize the size first. And then if we are loading, we need to make sure that we resize appropriately. That's the if const expert check in the middle there. And then we're going to go for each element and then serialize each element recursively. This is the part where if you have a std string, you would iterate manually over the bytes and cause the compiler to just blow like a memcopy implementation at your code. Again, I'm keeping it like this for simplicity. Hey, so if we're none of this, then we must have some type that has their own serialize, and then it's going to send his members to us, and then we are going to serialize those members, and recursively this is going to work because eventually we'll reach the end of the basic like fundamental or whatever types that this type consists of, and that's it. Then we're done, okay? And now that we're done, we must do a comparison, right? Because if we just wrote a brand new C++ serialization library, it better be zero overhead. So let's compare it with our handwritten code. I'm just going to go here, okay? On the left side is the handwritten code. On the right side is the code we just wrote, okay, with the archive and stuff. And when I go read the data, I see even though the size serialized is the same, the format is the same, everything is equal, here it's equal, here it's equal. On the left side, it takes 879 milliseconds, and on the right side, it takes 1.2 seconds. It's almost 50% overhead. Where did that overhead come from? We're just writing template C++, like C++20. We didn't do anything. We didn't call virtual functions. Why? Is that the end of C++? So I'd like to check the assembly to understand what went wrong here. And I see a huge difference, but I don't panic at this huge difference. I want to kind of scroll down gently until I get to, let's see. OK, I see on the left side like a few mem copies, OK? This is the handwritten code with the mem copies. And on the right side, OK, we reached already the deserialize function, so I will scroll up. I can see that there is a jump here, OK? There's a call to a function. And this function is the, let's go right. OK, that's like one of the things that's great about C++. OK, so this is probably, OK, this is serialized many, OK? So we call serialized many. So we started to do the serialization. We get to the call operator. The call operator probably got inline because we don't see it, but the serialized many didn't get inline. And this is where I kind of think to myself, hey, isn't this too much to ask the compiler to really guess that we're going to benefit so much from inlining the code, like 50% benefit from inlining the code, because the code is some kind of recursive. So how can the compiler know 100% that it's worth to go do the work at inline? Unfortunately, I think it's too much to ask the compiler at this point. I don't know a solution. Maybe there's a compiler author here who knows the solution to this, because this gets like the serialized many calls serialized one, which was called serialized many, is like can go like this for 5, 10, 20 times. The compiler not necessarily going to know that they need to inline it. So we're just going to use force inline, guys. So I know it's not standard, but this is like the tool that is working for me in ZPP bits. And once we use this force inline, we're going to force the compiler to do the work. And then the compiler is going to discover that, hey, I can optimize it so good because now everything is available in the inline function, and everything optimizes so well. I want to show you this also here. This is the secret, guys. Okay, so here it says it's 7, 8, 9 milliseconds with the force inline. Here's the force inline at the top, and we add it to almost every other serialized function to make the compiler work hard and do its job. And now the compiler is generating code that even look like faster than the handwritten code. And I want to show why. And I think this is kind of it's not true in all of the cases, but remember this like for loop that inlines even the memcopy if you do that like for byte in a string. So that's exactly what happens here, because you can see this memcopy here. We don't see it on the right side. And the reason is the compiler just inlined even the memcopy because there's no memcopy. There was like a loop for each byte in a string, and then the compiler figured, okay, I'll just put memcopy in there. So that's why maybe this was a little bit faster in this case, but hey, this is equivalent, and I like prefer usually to just go for the memcopy because look how many assembly instructions are here. This can blow away, but we can always configure however we like with inlining of memcopy, without. We can do whatever we want with ifconst_expr. Okay, so now that we know how to achieve the zero overhead, it's time to make const_expr everything. I'm not going to discuss a lot of the details about this slide. This is basically taking memcopy, doing stud bitcast instead. You can imagine this template was instantiated with some kind of integer, and then we do a bitcast of integer into an array of 4 bytes or whatever size of int are there. And then we do a stud copy n. The stud copy n threatens to have the same problem as the memcopy had, but we can always distinguish between runtime and the compile time implementation by using like if stud is constant evaluated and then go for the memcopy in the runtime if we want. But that's, again, everybody wants something else, so this is why we have ifconst_expr. Let me go next here. So a little bit about reflection, because we don't want to write our code like this, okay? There is issues with like asking developers to write all the members and then they end up doing something else instead. So that's why C++20, and there's many libraries that attempt to do it even before C++20, and there's magic get that I heard before the talk. There is like boost something, I forgot the name. So all of them kind of let you do some kind of dummy reflection in C++. The way I did it is fairly similar to the others, except I kind of didn't want you guys to look at like recursive templates and this kind of stuff. I want to give you something very simple to look at. So let's take a look at those variables. So we're defining one variable of each type in our class, and I want to show you that you can just do structured binding with each and every one of them. But this is not true for just our class. It's true for almost any class. You should read the structured binding protocol requirements for structures and then understand if you can do this. For most types, this works, guys. So once you do that, you kind of tempted to go for the variadic kind of thing. And if you can do this variadic kind of thing without knowing the number of members, then our serialize one function from before has another else, has another condition. And the condition is, hey, if this type doesn't explicitly mention the members, I'm just going to go for structured binding and decomposite the members. And that's just it, right? It's 2 lines of code change, and now we have reflection in C++. Well, we don't have this available yet, unfortunately, but this is a feature that is proposed. And you can read this paper. Structured binding can introduce a pack. It's great. I think it just became the most important feature for me in the next C++. So this is going to do the job. But we can't, okay? So we need to do something else. And unfortunately, we need to resolve to something that looks like a stud apply on a tuple, or tuple, I don't know how to say it. So depending on you. So basically, this visit members is kind of acting like a stud apply, but on structures. How do we implement these visit members? Sorry. So the implementation is not going to be very, very trivial, but we can do some manual work and kind of implement it, assuming we know the number of members. So notice that there is like a chain of ifconst_expr kind of stuff, that if the number of members is 0, I'm just going to return nothing. And then if it's 1, I'm just going to visit on this member after I do the structure binding. If it's 2, if it's 3, you get the idea. You can do it up until whatever your implementation limits or whatever you want. I mean, nobody, I guess, I don't want to say anything that is too kind of, I don't know if anybody has like 100 members in a structure, but if you do, you can extend it. Hey, so how do you get the number of members? And this is actually a tricky kind of piece of code here that tries to get the number of members for extract. And what it does is, except for the empty case, which we kind of return 0, it tries to construct this kind of lambda inside a requires expression, inside an if const expr, because the structured binding, we cannot put it directly in the requires expression. And this is not good. This is not working in, not supposed to, I don't know if anybody read the standard and came into a different conclusion. This is not supposed to work because the body of the lambda is not like the immediate context. So whenever the compiler is going to see the first line, let's assume your struct has 2 members, it's going to say, what are you doing? You're trying to do structured binding for 1 member, but I have 2 members. So I'm just going to throw a hard error at you, even though you're inside the requires expression, which usually evaluates to just false if the code doesn't compile. Actually, this code actually works, though, on Clang, right? When I tested it, but I think there's also a version of this that works on MSVC, but GCC just throws a hard error, so we shouldn't do that, okay? We should wait for the variadic structured binding, okay? But there's yet another thing we can do. We can introduce an any class that has like a cast operator into everything, and this is like where most open source libraries and Boost and kind of all these kind of libraries are doing the same thing, except I don't do it like in a recursive way. I want to give you a simple example to go home with, and this is the way that I chose to do it. So basically, the number of members, we try to construct our type with however number of any items that we want. It can start by 50 if you want, and then it will go backwards. The reason for the backwards is because even a class with 50 members can be constructed sometimes with 1 member, so we want to go backwards. It's not accurate, okay? So if you have a constructor, if your type is not an aggregate, it's not going to work. And we even have a workaround for this, in which case, instead of putting like all your members in a serialized function, if you can just give me like 1 line that tells me how many members your struct has, then the visit members will work. So at the worst case, you put just like 1 kind of, okay, there's phone ringing. I thought it was mine for a second. Okay, you just put this 1 line, and then it tells you how many members you got. Okay, so this is probably, we're getting near the end of the presentation. The remote procedure call that I mentioned earlier during the first few slides is basically where I think it's not worth it to invest time and implement a serialization library and not actually provide the developers or the users some way to call between different kind of functions, between different programs, different computers, whatnot. So as it turns out, my serialization library, it supports, like many other serialization libraries, to serialize a variant. And imagine that you have this variant of all your operations you want to do remotely, okay? So how you would do it is implement the operation like this. You put a normal structure, you put a call operator, and then the call operator is going to do the remote kind of thing, return the result gets serialized, and then everything is going to be fine. So how to do it? Basically, this is the syntax if you want to use a variant. This is a nice syntax. You basically go ahead and create this RPC add numbers. You put x equal 1, y equals 2, and if it fails, you throw exception. Then you transport this over to the server, and the server will actually create an RPC, which is just a variant, remember, and try to deserialize the variant. And on the serialization, it will check, hey, I see variant index 0, so it must have been add numbers, so I'm going to deserialize add numbers. Next, here we go again. Next, we're going to output the result of visiting that variant. Once we visit that variant, we're going to surely land on the add numbers, and we're going to return the call operator on that add numbers, which returns x plus y, which then goes back into the output archive, which sends the results back to the client. And the result is basically x plus y equal 3. This is not a good syntax, but this is like kind of a stepping stone for us to do RPC with just regular serialization library that supports variant. But how we can enhance it a little bit is by basically using just the functions instead of doing the call operator kind of thing. As it turns out, visiting structures in C++ is a kind of hard problem, but understanding the signature of the function is not. So if we understand that the function is receiving 2 integers as parameters and returning an integer, this is just easy work for us. We can just write the code that does that and wrap it in a nice way, such as this. So instead of the variant, we use this kind of ZPP bits RPC type, which receives like bindings. So add numbers is bound to 0, multiply numbers is bound to 1, and you can bind it to anything you want. The thing is that the client is now need to use better syntax rather than using input and output of just bytes. We can just wrap it nicely in a function call, and then inside the function call, it will serialize the 1 and 2. Like regular 2 integers, it will be like 8 bytes if int is if size of int is 4, and it will be transmitted to the server. The server is going to also have like an RPC server type that helps wrap. It's just thin wrappers. There's nothing going on behind the scene. It's going to serve the request, and within that serve, there will be some kind of implementation similar to std_visit, which will then call the function, return the result, and serialize the result right away into the output archive. And then the client can receive the data from the server and basically ask, hey, I want a response for 0. The response is clearly an int because the function returns an int, and then get the response and work with it. Why would I write, however, those 0 and 1 numbers? I can do something better. I can just put like a string, but the string will introduce overhead. So what I do is basically I implement a SHA-256 function. I can implement whatever I want. You can implement whatever you want in compile time to return you an ID. And if that ID ever collides, it will just not compile, because you can check this in compile time. I'm not going to show it here. I'll point you towards the repo, but it's amazing to see that you add like 2 bindings with the same name, and then immediately your code doesn't compile, and you're getting properly diagnosed about it. OK. So this is probably the last. Oops. You OK? OK. So I spoiled it for you a little bit, but this is probably the last technical slide. There's many more features that I would like to show you. But hey, who said that if you invent your own protocol, it will not just be able to mimic like a known protocol such as Protobuf and then immediately work with every language that Google like implemented Protobuf for? So this is the areas where I want to show you, not that I implemented Protobuf that is freestanding, but to show you that, hey, you can put whatever protocol you want with if-const expert and with some flexibility and some sense of design, and it will do amazing things. And I want to actually run a comparison. Even though I promise you I didn't optimize the Protobuf code, I would like to show you still here a compiler explorer for it. On the left side is Protobuf. On the right side is this freestanding Protobuf. Okay, the way you do that is just, as the slide said, you just add 1 line and you're immediately into Protobuf. And the result is, notice that I can return the size. And for Protobuf, I think I need to do something extra here. So I just return 0. I didn't want to have Protobuf do extra work. But for me, I can know that this is 110 bytes, including like a 4-byte size prefix that I put. And then it is equal. It is taking like 2.9 seconds, and the Protobuf taking 3.4 seconds. Before optimization, I didn't optimize it. I just throw an implementation in there, and it worked. I ran some tests, and that's it. And I'm showing it today because I wanted to show you that you can do everything in compile time and not incur any overhead on the other use cases where you can't like use exactly Protobuf because it will be too slow for you. OK, so I think we are getting towards the end. And this is where I would like to kind of summarize what we achieved and what is still not good for us. First thing is I hope I convinced you that this is 0 overhead, and now that you guys can also do it because it was really, really simple code, and the code is going to be available for you in the presentation. It is completely freestanding, and I will take 10 seconds to show it in some kind of small demo. It is simple to use because most of the time you don't need to add anything to your class, or maybe just add the number of members. And in the future, maybe you don't need to do that as well. So C++ 26 kind of thing. What is still not good is basically I needed to use the force inline and the always inline. This is non-standard. And it kind of causes issues when you have like a class that, goes the other way around, and you have kind of secret dependency, and you need to somehow detect that with some kind of concepts. But I invite you to look at the code. It's not like that complicated. It's kind of just doesn't fit the slide, unfortunately. And I don't know how to do the auto scroll kind of thing. And I think for the better. And I think, yeah, the P1061 is where the variadic structure binding can really help us. Hopefully, next version of C++. So, hey, just one demo for the freestanding. If you want to take a picture, this like below is the compile flags for the freestanding mode. I needed to kind of reverse engineer a little bit how system calls work on my version of macOS. So, hey, this is the main function. It's compiled down below with no stdlib. And if I just run this, it will print freestanding example. And you can see here, it prints. This is like the system call for printing. And below, I needed to have some heap and some stuff like that. So, hey, you can go ahead and once I upload the presentation, I put a Godbolt link with the full code that's on the slide. It's probably not going to work on your system, though. So, hey, so thank you so much for coming and listening to this. And let's do some Q&A.
Thank you so much. I have a question. As you said, that implementation, like a really simple one. I mean, if I would want to implement something like that, I could do pretty much the similar or something like that. So
in 10 minutes. Sorry for interrupting you, but it's really like very, very short code, and it's really, really fast.
Yeah. And because of that, my question is, are you sure that like other libraries do the same stuff? Are you sure that they do not do some, I don't know, smarter stuff, or they probably work with something else? Because it's like looks weird that these guys who in Boost or any other libraries, couldn't they do the same? Or what's your sort of?
Everyone here can do the same, and online, like everyone can do the same. I guess not everybody did the force inline aggressively enough to achieve this kind of results, and that's why.
Yeah. Okay, thanks.
Oh, another kind of statement there for your question. It's not only the force inline that does the magic, even though it looks like in this session it did. It's kind of the toolbox. There was the toolbox slide that I showed, and a lot of serialization libraries are just not using the toolbox, so they pay for virtual calls, they pay for something else, and that can answer the question as well.
Okay.
Yeah. We have a question from online attendees. Yes. Eric Huber asked, how does this handle endianness?
That's a great question. You should just go ahead and click the link, and there is like an if context pair that does like if you are big endian, if you send, like we said, there's 8 bytes kind of thing. So you can say, hey, I want big endian instead of std copy, it does std reverse copy or something like that. So it's like the amount of flexibility you get here. I wanted to show the Protobuf and not the big endian example because the flexibility is everything. You can do everything you want. Yes.
Yeah. Another question that is kind of solved in other serialization libraries is versioning or schema versioning. How hard would it be to engineer this into your library?
Amazing question. First of all, I went like nuclear by just giving you the Protobuf implementation. So Protobuf supports this kind of backwards forwards compatibility. But if you want to do explicit versioning and not use the Protobuf and not pay for that, you can definitely just go for std variant of, hey, version 1, version 2, and you can put even the hash with the int or whatever you want to version it like. I hope that answers the question.
You said you had some problems with Lambda in GCC. What I don't understand, why do you need Lambda at all in that case?
This is a complicated question. I want to say that I will answer it later, but I'll give you one sentence of an answer. You can't put the structured binding in the requires expression directly, because the requires expression require an expression in there, and the structured binding is not an expression. Okay. So that's why you kind of need to go for the lambda, but it works on some compilers, but I don't believe it's the intent of the standard.
Hi, I had a question about, like, if you have different messages, if you have, for instance, Protobuf, like I can just put in a message and it'll deserialize the right type, I guess. So do you have any support for that, or would I use a state variant to just say the first message can be whatever?
Not sure I fully understand it, but it sounds a little bit complicated. I can answer this. The Protobuf protocol that I implemented is identical, or tries to be identical to the Google one. So I was able to, one of the examples in the repository, if you click it, you will see like Python serializing something and then deserializing C++ with Protobuf.
Okay.
I hope that answers it.
Yeah, I think so. Thanks.
Another question from online attendees. Yeah. How difficult would it be to compile it with older C++?
I only caught the first part when you said how hard would it be for the third party too.
How difficult would it be to compile it with older C++?
In older C++. Okay, so this library has a ton of concepts and ton of if const expr requires whatever. So you probably don't want to directly just put it in older C++ and try to compile it. But you can take the example from the slides. You can just put some spin here and there, and it will probably compile in older C++. Oh, another question from online? Or? Yeah, go.
This is just a comment, but the having gone to the Lambda talk, one thing that 23 brings in is use of lambdas in unevaluated contexts like decal type. Right. And that might be why it works in Clang if they already implemented that. It may be a support that comes in with 23, essentially to do what you want. I don't know if it's exactly the same or not, but
that's what I thought actually. That's why I tried to do it, and then I went ahead and read the standard. And actually, the standard doesn't care if it's in unevaluated context. The issue is where the error for you to try to unpack, like let's say a struct with 2 members and unpack it into 1 member is structured binding. This causes a hard error. It's not a spin error. Okay. And it's true that you can put the lambda there, but it's going to be a hard error, even though it's unevaluated context. Okay?
Thanks.
How would you deal with multiple references pointers to the same object?
Okay, that's an amazing question. I don't deal with that. The thing is that I really believe that having weak references and pointers in the serialization library can very easily lead to, hey, let's say I send you malicious content, and then you try to parse it, and then it will lead to some kind of weird undefined behavior. So what I do instead, I go for only owning types. So you can have like unique pointer, you can do graphs, you can do even circular graphics if you want, but will not be like a raw pointer or reference. It will be just a unique pointer or something similar to a unique pointer via the concept.
Libraries like UCI have message structures that have member counts on the order of 1,800 or more. How feasible might it be to parallelize serialization?
Okay, to parallelize this, I haven't thought about it, but I guess I don't want to give like draw an answer, but if I had to draw an answer, my answer would be you can probably partition your data in such a way that you do individual calls to serialize. And let's say you have like a big list, so you can divide the list and do something like that maybe. But I don't have a full answer, sorry. Okay, I think we're just at time, correct? Okay, thank you so much. And here is just like the last sentence for you to remember. And now thank you so much.